In classical physics, the world as we perceive it daily, described by scientists like Newton and Maxwell, nature was strictly divided into two clear categories: waves and particles. These two entities were entirely separate, possessing distinct properties and behaviors. Particles are discrete entities. A particle has a specific position in space, a specific mass, and can be measured as a local impact or an atomic unit. Think of a billiard ball, a bullet, or a grain of sand. When we fire particles through two openings, we expect to see two distinct lines formed behind those openings. Particles obey the laws of classical mechanics. Their motion is predictable, and by knowing their initial position and momentum, we can accurately calculate their future path. Waves, in contrast, are not local. They are diffuse and spread out over a region. Consider waves in water or sound. A wave doesn't have a specific position. Instead, it is characterized by its wavelength, frequency, and amplitude. The fundamental property of waves is interference and diffraction. When two waves meet, they interact. They can either reinforce each other, constructive interference, or cancel each other out, destructive interference. This property leads to the creation of characteristic patterns, e.g., bright and dark fringes. Diffraction. Waves have the ability to bend around obstacles or spread out when passing through small openings. When a wave passes through two slits, it doesn't separate into two distinct segments. Instead, each slit acts as a new wave source. The two resulting waves interfere with each other, creating an interference pattern on the detection screen. The collapse of the classical dichotomy. For centuries, this separation was absolute. Light was a wave, as Young demonstrated, while matter was particles. This dichotomy formed the core of classical physics. However, in the late 19th and early 20th centuries, a series of experiments, such as Albert Einstein's explanation of the photoelectric effect, which showed that light can behave as a particle, the photon, and the confirmation of the wave behavior of electrons by Davison and Germer, led to the collapse of this classical division. Quantum mechanics taught us that, at the subatomic scale, the two worlds are not separate, but interconnected through wave-particle duality, a phenomenon most strikingly demonstrated in the double-slit experiment. This fundamental difference between the classical perception, separation, and the quantum perception, duality, is what makes the quantum paradox so difficult to grasp with our everyday common sense.